First of all, thank you for coming out and attending the CC430 presentation. Today we're going to be talking about the CC430. It's an exciting new product from the kind of a collaboration, if you will, between the MSP430 groups inside Texas Instruments and the low power wireless teams. My name is Miguel Morales, and I'm had the pleasure of working with the new product on the new product development team for the CC430. I'm an applications engineer in the worldwide MSP430 applications team. And with that said, I think we'll go ahead and get started. So in terms of the agenda today, we're going to talk a little bit about where the CC430 fits kind of in the grander scheme of our current wireless transceiver offerings. As TI, we'll talk a little bit about RF system and what's involved, where the CC430 fits in terms of frequency and even to some degree application space. We'll show a block diagram and speak to some of the new peripherals that we have on the CC430 versus some of the previous MSP430 families. Then we'll come in and focus on the radio. We'll talk to, it's a very flexible radio, lots of different features, and we'll talk to some of those. We'll show you what you will actually have available in terms of the release to the market, and at the very end, of course, a tool discussion in terms of what we give you to work with the part. So if you look at TI's portfolio overall, it's actually quite broad, and especially in the wireless space, we have I think a good way of breaking it down would be the sub 1 gigahertz and the 2.4 gigahertz. In the 2.4 gigahertz space, of course, you have a worldwide frequency band that's unlicensed, and so there's a lot of different standards that have chosen that frequency band, and of course we have that these products in terms of the remote controls, RF for CE, you see there 2530 and 25. So anytime you see a 25XX, it's actually going to be a 2.4 gigahertz radio. We have some wireless audio products, sports and gaming. And then as you get over to the left, you start to see some of the sub 1 gigahertz products, and that's what we're talking about today. The CC430 is a sub 1 gigahertz transceiver that's been integrated in with an MSP430 MCU. Specifically for those of you who have worked with TI products before, it's the CC1101 transceiver. So just in terms of positioning relative to some of the other products, I felt this was a good slide. And it has some of the example applications here. You may see it in some smoke detectors, heat cost allocators, sub-metering applications. This is, I believe, is a motion sensor that we have there on the slide. So what is the CC430, right? I spoke to it a little bit in the sense that it's a sub 1 gigahertz RF transceiver. The CC1101 radio transceiver that was integrated in with the MSP430 is known, in terms of its key value propositions, to have high sensitivity, low current consumption for the performance that it delivers. The blocking performance, so its performance in a noisy environment is really good. Very flexible data rate and modulation. It supports frequency modulation, amplitude modulation, data rates from 1.8 up, I believe, up to 500 kilobits per second. So power output, and we'll speak to some of these specifics a little bit later in the presentation, but it's a very flexible radio and is backwards compatible. And one of the frequent questions that we get about the CC430 is, does it work with the previous devices, with the CC1101? So if I have a 2-chip solution with MSP430 and a ChipCon CC1101, will the CC430 still work? And the answer is absolutely yes. It's the same radio, so everything still applies, and that was definitely something that we paid close attention to in the development of the CC430. So it's partnered with an MSP430 MCU, and more specifically the new generation of MSP430, which we're also very excited about, that we call the 5XX family. 5XX family, just like all previous MSP430s, has an intense focus on ultra-low power consumption, high degrees of analog integration, and the integration of high-performance analog. So we've got ADC 12 on this part, samples up to 20 kilosamples per second, and comparator B, shared analog reference, and we'll talk to the block diagram a little later, but high degrees of integration that really simplify your application in terms of other components needed, and hopefully ends up reducing the overall cost of a customer design. But what I hear from a lot of customers about MSP430 is they like how easy it is to use. And from the tools that we put around it to the actual architecture itself, I agree it's a very, very easy microcontroller to learn and to work with, and the 5XX is absolutely no exception to that. So as a native 16-bit CPU, it actually fits very well with many sensor interfaces, because many of the sensors that we deal with really don't require much more than the 16 bits. So that native 16-bit architecture tends to fit very well with sensor applications. Mixed, of course, with the ultra-low power, you end up in battery systems. We felt it was just a really good fit for the low-power RF IC like the CC1101 and the MSP430. So it's fully integrated. I know sometimes the question comes up, Miguel, is it a multi-chip module? And the answer is no. The mailbox, if you will, between the 430 and the radio is fully integrated into the MSP430 memory map, and is accessible just like any other peripheral, like a timer, if you will, or a serial communication module. So it's a fully integrated SoC, low power RF SoC. In terms of how you mix the hardware in the past using TI hardware versus meaning the microcontroller and a radio transceiver, we have a lot of different options at TI, right? And wanted to make sure that everyone understood where the CC430 could be a good fit. And so this slide kind of details, the three components, if you will, of an RF system. You've got the radio transceiver, that's just the physical communication between devices. You have the software layer, which is going to be specific to the wireless protocol. And you can split up the software into two pieces, right? The wireless protocol, which means you have, a 6-low PAN, a wireless SMBus, and then you have the application, which is whatever it is you're doing, heat cost allocator, or sub-metering application, etc. In the past, we've had two-chip solutions with the MSP430, where either the MSP430 is connected to another SoC. In the past, we've had, for example, the CC430, which has the integrated Zigbee, right? And you have this very small footprint interface that just lets you configure what is essentially a Zigbee black box. And so that would be the protocol processor. And the CC430 does fit that mold quite well. You could load a protocol onto it and have an external application processor. There's definitely some benefits to that in terms of offloading any wireless protocol requirements or impact on the real time, just putting that all into a protocol processor. So the CC430, being a smart transceiver with the integrated MCU, is capable of being a protocol processor. So it can handle the wireless protocol and the radio PHY. We also had the option, of course, and many customers have been successful, for example, with the 5438 mixing it with a 2520. But the point being here in the application MCU plus the RF radio, that the radio is just the physical layer. It's just a radio. It doesn't have an integrated MCU, and you send it all the data that you transmit and receive all the data back from it over the SPI. But the CC430, I think, it really shines when you can do everything on the chip. And so there's no need to get the two devices. It's the full SoC. It has enough bandwidth operating up to 20 and 25 megahertz to do whatever you need in terms of the application as well as your wireless protocol. And of course, it's got the integrated radio, so you can do everything in one. And it opens up the door, I think, to a lot of the applications that we see today, but hopefully simplifies that development because it's all on one platform. So some of the different application spaces that we see for the CC430, consumer and home area networking. So there you have a guy running down the street, wherever, a park, I guess, and he's got CC430 in his watch, for example, and it's communicating with a chest strap, or it's communicating with an accelerometer, that he has tied to his foot that tells him distance and speed and all those things. Home area networking is another big opportunity for that is definitely one of the emerging markets in terms of smart home networks, right, that automate the lights turning on based on the motion sensors, the temperature control in individual rooms. So there's a lot of emerging applications there that we're really excited about, and the CC430 is definitely capable of that. Remote monitoring, in terms of sub-metering, communicating outside in the sub-1 gigahertz space can be very attractive because you can go longer distances, you don't have as much environmental noise into the network, and so any kind of remote monitoring and the ultra-low power, is a key value proposition here for the MSP430 and the CC430 because let's say you have all these sensors on a bridge, you don't want to go crawl up there and actually have to replace the batteries, if you will. So asset tracking is definitely an interesting one, and we're getting more traction as time goes on in terms of asset tracking, specifically the partnering with the with RFID. We're looking into the -7 protocol, of course, with the CC430, and so we're in all of these cases, we're trying to really pull in a lot of third-party activity, and I think you guys will see that more and more as we roll out the CC430 to the market. Opportunities like -7 and 6LoWPAN and wireless MBus, all these is a strong third-party network that we're building to try and make it easy for you guys to attack these markets, and get to market fast. So that's kind of the brief introduction to where we see the CC430 in the market, and let's talk a little bit about an RF system. What is it? What can you expect an RF system to look like with the CC430? So of course you've got the RFIC. We'll call it the CC430, and when I say transceiver, I don't know how new you guys are or are not to the wireless space, but you've got your transmitter and receiver both on chip, so we call it a transceiver. The microcontroller is integrated. We've got our 5XX, our 5XX core. The crystal, in the case of the CC430, it runs off of anywhere between a 26 and 27 megahertz crystal. It does have a balanced output, so if you have a single-ended antenna or an unbalanced antenna, then you have to have the circuit that matches the impedance to that antenna, and so we call that a balun, and it effectively does the impedance matching between the antenna and the balanced output or input of the radio. And in some cases, especially for specific regulatory requirements, you're going to have some extra externals out there, bandpass filter, to improve the selectivity, if you will, and make sure that you're not emitting or receiving in any band outside of the regulation under which you're operating. Of course, you have your antenna out there, and there's a lot of different options in terms of antenna. Of course, you have the whip antenna, which is what we provide in the kits. You've got your PCB antennas. You've got your chip antennas, and they all kind of have their trade-offs. As many of you well know, that's whole presentations in and of themselves. But, I figured it was good to give a 1,000-foot view of what you'll see in your typical CC430 system. Now, it's important, I've talked about 2.4 gigahertz. I've talked about sub 1 gigahertz. It's important to understand that CC430 is a sub 1 gigahertz radio. So it doesn't operate, for example, it's not a worldwide radio, right? The sub 1 gigahertz space is unique in that it has, it's more tightly regulated, kind of country per country, or region per region. So here we have the map of the U.S. It has the 315 and the 433, 915. In Europe, you get the 868 version and the 433. And at the very bottom there, I think, is the key piece of this slide in terms of what the CC430 supports. It's the 3 to 348, 387 to 464, and 779 to 928 megahertz. And this does have some implications on the different wireless applications or the different networking protocols that you can apply. So as it stands today, TI's Zigbee solutions and in fact the modulation that you have inherent to the radio and everything separates what we call the 802.15.4 protocols, which does include Zigbee or just 802.15.4 is separate from the CC430. What you'll tend to see is that many companies in the sub 1 gigahertz space have either their own standards or they've developed other industry standards. But it's not Bluetooth, it's not Wi-Fi, it's not ultra wideband, and we're talking about the effective data rate here at the bottom of 1K to 100K, and then the range that you'll actually see. So it's short-range wireless, but you have within that space a number of applications, and we've talked about some of those already: building automation, residential control, industrial, tracking, sensors, home automation, meter reading. And so that hopefully clarifies even further our the positioning for the CC430, if you will. So let's talk a little bit now into the block diagram. What do you get in a CC430, right? So it's based off of the 5XX core, and so you have a 5XX core logic there. And I'm going to start from this green box there at the top and kind of work my way around the circle. Unified clock system. The MSP430 clocking system, it's the same as any other previous 430 clocking system. You've got 3 clocks. Your M clock supplies the CPU. Your SM clock is kind of your fast peripherals, and your A clock is your slow peripherals, or your 32 kilohertz signals, right? And your low power modes, how the 430 and the CC430 really achieve extremely low power is by turning off these clocks in succession. And so in the LPM3 mode, you have your A clock or all your slow peripherals enabled, and you can actually operate this down in the 2 microamp range and have an active real-time clock. Any slow peripheral, you can have some serial communication at lower speeds, maybe 9600 BPS. But there's a lot of functionality still in LPM3, and a lot of that's based on the unified clock system. DMA, it's got some DMA channels in there. It's a new version of the CPU. It was kind of optimized for the core. The enhanced emulation module actually allows you to do a lot of cool things in terms of combining breakpoints that unobtrusively and in hardware allows you to see exactly what's going on in the application without interrupting the real-time behavior. So it's a very cool emulation module, very, very advanced debugging capabilities. Power management, the 5XX core does depend on an internal LDO that has been integrated. So the core is actually separate from the external peripherals, and that means we have the internal LDO. The cool thing about that is that we can actually, we also built into that SVS protection, so you've got built-in SVS protection, and for very low power. You can have SVS protection for, I believe, like 200 nanoamps. And there's a higher power mode if you want faster response time for your SVS. You have the option, but you can have SVS protection for 200 nanoamps, which I think is a great achievement. Got some timers on there, fully functional real-time clock. It's got alarms. You can actually compensate for temperature on the real-time clock. Serial communication module that has both synchronous and asynchronous channels, meaning you can run both an I2C and a UART simultaneously using that same USCI, we call it. LCDB, AES, so LCD support for 96 segments. And we're going to have some flavors with and without the LCDB support, so if you don't need it. AES encryption, this is also a big plus, I think. We added the AES 128-bit encryption. This encryption is the encryption standard that the U.S. government uses. It's very secure, especially when you build it into some cipher blocks. Of course, we have the radio module there on the right. We have up to 5 ports of I/O. We have an integrated reference module, which is a shared reference for all of the analog peripherals on the device that's stable over temperature. Very excited about that. ADC12, very low power, high performance ADC, a new comparator module, a port mapping feature, checksum, and a hardware multiplier. I'm going to talk a little bit about the port mapping, but as well as the flash and RAM requirements. It's a little hard to read them right now. So CPU, the CPU of the MSP430 has it's inherently a 16-bit microcontroller, right? But we extended the memory space on the 5XX so that we could move up into the 128, 256 kbps. Not kbps, at 256 kilobytes. So in order to do that, we actually extended the CPU to handle 4 more bits. It turned into 20 bits. But you've got 16 working registers, which is a ton of working registers. And this is actually very C compiler friendly. It allows us to optimize our code in the compilation to much smaller sizes than many of our competitors. And when I say it's C compiler friendly, it also has atomic instructions, which is cool because you can modify 2 variables in RAM, for example, you can add them to each other without bringing them into your working registers. So that's kind of how we start to get some of these code saving. You don't have to bring everything into your working registers. But if you do, you get 16 of them. So it is fully instruction compatible with all previous MSP430s. If you learn the instruction set before, you know the instruction set now. There's really nothing different about that or incompatible with the previous devices, meaning if you have an existing 2-chip solution, let's say you have a 2274 and like a CC1101, then most of that code is going to be applicable here, which I think is nice. CC430 memory map. We changed this up a little bit, not very much, but I think we added some really good features. We've got our peripheral memory down at the very bottom. We have a new BSL segments. So BSL is just like any other flash, but we use it and it's lockable for the bootstrap loader, which allows you, after you have essentially blown the JTAG fuse, and means you can't access the device through JTAG anymore, you can still access the device with the bootstrap loader. But this bootstrap loader is reprogrammable flash. So we intend to provide you a library, and with that library you can select your interface. You can reprogram the interface of the device, which I think is cool. You can reprogram to I2C, you can reprogram to SPI, you can reprogram to whatever frequency of UART you desire, and we have that memory allocated for you, and it's fully reprogrammable. So by default, you get a 2-wire timer UART, operates at 9600 BPS. But yeah, and so in terms of security, it's also really good. You you can access the device and you can make it such that you write the password, and if you get the password wrong, it erases everything in Flash. Or if you like it, you can disable the BSL altogether, and you can actually use it for program memory. So it's very flexible. It's just more Flash, but it's lockable for the BSL. So that flexibility, I think, is a big improvement over some of the previous families that we have. Another improvement that we had for any of you MSP430 users out there, we used to put factory calibration data inside our segment A. And customers would get frustrated because they would delete that factory calibrated data, and then it's gone. You can't do anything. So we actually move that out into its own factory data section, and you now have these 4 user info segments. These are just like any other Flash, but they're just a little bit smaller, and they're always going to be at the same locations for all devices. So that's not going to change. And oftentimes customers, user info segment A is also lockable. So if you do like a mass erase, you can go ahead and put your application-specific calibration information in there, and it won't be erased because it's lockable. But the factory data has a lot of cool stuff like device unique ID for each device. You can see the peripherals that are on that device. There's a peripheral discovery table, if you will. We put in calibration data for the ADC12, for the temperature readings. We put in calibration data for the reference module. A lot of good stuff there in the factory data that I think you guys will find useful. RAM, you have up to 4 KB on the CC430, and program memory, you have up to 32K on the CC430. So I believe that's everything on that slide. But unified clock system, this is actually what I was talking about previously, and is what allows the CC430 to operate at very low power. 6 independent clock sources, and we'll kind of step through them. You have the low frequency oscillator. So this is an ultra low power, low frequency oscillator. It's where you put your 32 kilohertz crystal. We have a very low frequency oscillator, which is a internal 10 to 12 kilohertz. It's not very accurate, but it's really good at waking you up every now and again, right? So if you need real-time clock precision, you're not going to get it out of the VLO, but it's really good for just a periodic wake-up. We also integrated a REFO, and the REFO is a 32 kilohertz signal, internal oscillator, that is a great backup, for example, for if your crystal goes out, your low-frequency crystal goes out, and you have a fail-safe now 32 kilohertz signal, or if you don't need the accuracy of an external crystal, then you can use this internal 32 kilohertz REFO to just operate without the crystal, because it's 32 kilohertz. In terms of high-frequency sources, we have the XT2, which is in this case, it's the RF crystal. So you're going to have a 26 megahertz crystal out there. It is a DCO with which we wrapped in an FLL, so frequency lock loop. And that frequency lock loop can accept into it either your crystal 32 kilohertz frequency, your reference oscillator, or your XT2 oscillator. So very flexible clocking system. Any of these really go to any of the A clock, M clock, or SM clock outputs. And as I was telling you earlier, the low power modes are reached by turning off the clock to the CPU, by turning off the clock to the high frequency clock, and then in the end by turning off the A clock. And so that reaches you to the lowest power mode, which we call LPM4. We do have this other kind of standalone oscillator here we call MODOSC. He's about 5 megahertz, and we use him for the ADC12 and for the flash controller. And what I like about him is that he will, he's on demand. So you don't have to worry about it turning on. If you've selected your ADC12 to be sourced from the MODOSC, or if you're writing to flash, you don't have to go in and make sure that you have the right frequency applied to the flash. It's on when you need it. It's off when you don't. And in fact, all of our clocks have that feature capable. LCDB, to talk a little bit about them, and the AES encryption. LCDB has a couple of cool features. You can program the frame frequency. It has an internal regulated charge pump. so you don't have to generate your bias voltages externally. You can do that all internally, and it can be independent of your current VCC due to the charge pump, so that's nice. It's good for the contrast and over temperature. You can actually blink individual segments. You have two, like a copy of the LCD memory, which is kind of nice because you can blink between them, meaning you can blink it on and off, or you can blink a whole LCD screen, right? It's just two separate memories that you move between. So very, very nice LCD support using the LCDB. Then you have the AES encryption module, which is interrupt capable, and it handles both the encryption and the decryption. And I mean, that's about it. What I like about that is that we also have a software library, right, on the AES. If you go on www.ti.com/MSP430 and you click on the Application Notes tab, we have a software library for AES encryption. But when you look at the cycles that consumes and the cycles that it saves you, I think it's in the thousands in terms of what this hardware module can do for your application. So in terms of MIPS added, it's just a great feature to have on the device. Port mapping. I like port mapping because it makes my life as a PCB designer a whole lot easier. I can take any of these, and I just took a little sample here of like the lower left corner of the device, but I can take any of these PM underscore signals. So here, for example, I have my serial communication, my serial clock, slave in, master out, slave out, master in, or my GDO signals from the radio, or my timer signals. And I can map any of these signals to any of the port mapped ports. There's 3 port mappable ports, and I can take one timer PWM and I can output it to 8 signals on that port, or I can mix it up in application if I so choose. And when I'm doing my layout, that can really reduce the constraints and the routing and maybe in some cases the number of layers that you actually have to use for your board, and that saves you money. So I think it's a neat feature for testing, for development, for the customization of your PCB design. I think it's just great. And so it's any digital signal can be port mapped out to port 1 through 3. And it automatically locks itself, or you can lock it. It is password protected, so your application doesn't go nuts and then all of a sudden start changing up your ports. And the comparator B is another new module that we have on the CC430. Pretty much this slide just speaks to the fact that we have a reference generator. So if you guys remember about the ref module, this is the shared analog reference. It has a little tap that goes out to the comparator. That can be amped up to 1.5, 2.0, or 2.5 volts. And then you drop it down through a resistor ladder where you get to pick a high and a low reference into the comparator. And then you can automatically switch between those two once you've reached those thresholds. And you can do this all automatically without CPU intervention, which in the end adds up to power consumption. This is very flexible for capacitive touch, for example, and we're definitely got a whole thing going on with capacitive touch and trying to make it easy in terms of software support and all that. But the comparator B, I think, was a great step in that direction, and hopefully you find the flexibility useful in your application. So the comparator output goes to the timer module. You can time these comparator events, if you will. There's a RC filter on there if you want it. Very, very flexible comparator. So that was the CC430 side. I mean the MSP430 side, the 5XX core. I want to make sure that we talk, of course, about the radio. This is a block diagram of the radio. We've got the interface to the MSP430 core, which we're going to discuss a little bit. We have two 64-byte FIFOs. We've got the transmit FIFO and the receive FIFO. It makes sense, but of course that means that your maximum in single packet size is 64 bytes, right? Your packet handler is an optional feature. The depend on the packet handler, or you can use the features of the packet handler, which has certain layers of filtering that we'll talk about, but it handles things like your preamble, identifying your preamble, identifying your sync word, and then passing the bytes into these FIFOs. Or you can choose not to use that and just tap in straight to the radio side. And so that's what we call synchronous and asynchronous communication on the CC430. We know that many customers like to use the packet handler, but there's also a set of customers that like to just send the raw data to the radio on the timer pins, and we absolutely have that available. So we got the modulator up to the frequency synthesizer, the phase splitter, and power amplifier, low noise amplifier back in. If you notice, this is a differential output, the RFP and the RFN, so that's why you have to apply the balun. And then you take it back in through the filters and the ADC samplers for the demodulation. So the resistor bias, there is an external resistor here required, and you have the 26 megahertz watch, or 26 megahertz crystal. So packet handling support. If you do choose to use the packet handler, then some of the features that it gives you is the support for preamble bit recognition, right? So the series of 101010 that kind of trains the radio to the incoming bit pattern. The sync word, which is user programmable, it'll identify those and then trigger an interrupt, for example, whenever it's received a valid sync word. You can filter incoming packets for length, for address, and for checksum. So you can take, for example, your network protocol is never going to have more than 10 bytes in a packet. You can set your length field such that if you receive a packet longer than that, then it's going to not wake up your MSP430 and say, hey, I received a packet. It's only going to put into the FIFO the packets of length 10. You can also send it to infinite length. You can set it to a maximum length. Very flexible. Address, I think, makes sense. It's either addressed to you or not. And the checksum, it either passes or it doesn't pass the checksum. So that packet handling support, I think, is a very, very nice feature. Once again, it can be disabled, and you can just communicate directly with the radio using timer signals. And we have those signals internally connected to our timers, both for the output and the input. In terms of the TX path, we have our power amplifier, and this is programmable from minus 30 dBm up through 10 dBm output to a 50 ohm antenna. So that's very flexible. It does have a built-in LDO, which is nice because that output power remains stable regardless of your DVCC or your AVCC. And as I've mentioned before, it does require the balun. The PA table, I think, is nice because it ramps up the power slowly and then it ramps it back down slowly. Because if you just go from 0 power to full power, you actually create some emissions there on the side in adjacent bands, which the different regulatory groups will come in and kind of get you for that. So this power table gives you intermediate values to step up to your maximum output power, which of course you can set. So if you only have to go 10 feet, you don't have to blast 10 dBm, and then it'll ramp that back down. And all these values are provided by the tools that we give you. So we have this SMARTRF Studio, which can give you every value you need to write into the PA table. You have to do no real calculations. You just set your maximum power that you want, and if you're doing amplitude shift keying, it'll spit out these values for the PA table. So that's very nice. Synthesizer generates required output frequencies, 26 megahertz to 27 megahertz. The frequency resolution is dependent on that crystal frequency, but you get down to 397 hertz, right? So very, very accurate frequency resolution for communicating channels, which is good, especially if you're doing, for example, frequency hopping implementations where you need to make sure that you're on that frequency for that period of time. This accuracy guarantees you're going to hit it, you're going to get it right. The modulator support includes the frequency shift keying and amplitude shift keying, but it's got variations of both. So you can do the 2FSK, the Gaussian to FSK, and then the minimum shift keying on the frequency side, and then you have the full scale amplitude shift keying, or just your on-off shift keying. The programmable data rates all the way from 1.2 to 500K baud, and supports automatic Manchester encoding. On the receive side, you get, of course, your RSSI, so your receive signal strength that is you can receive either periodically or you can lock it in after you received a valid sync word. It means that you have an RSSI value for the packet that is currently being received. Right, so that's useful. The carrier sense is cool because there's hardware support for listen before talk implementations. You can sense whether there is a carrier on the line before you go off and talk, right? Which makes sense, but it's cool because it automatically goes from idle mode. The radio will automatically go from idle mode into receive mode, and it'll check either that the RSSI is above a programmable threshold or that it's increased a programmable number of decibels. And it'll check, if I've crossed this threshold and someone's talking on the line and I don't move on to transmit mode. But if no one's on the line, then I do move on to transmit mode. And all of these state changes within the radio happen without the CPU having to come in, check the RSSI, then send the transmit packet. It's all automatic, and it's definitely a power saver. So that's what is shown here in terms of clear channel assessment. You also have a link quality indicator, which can be a secondary measure of the link quality between two devices. So you can rest assured that the signals that you're getting are of high quality and that the link is good. So this information, you can either go in and you can pull it from status registers, right, from the RSSI, CRC check, and the link quality indicator, or if you're using the packet handler, you can actually just include it. You can tack it on to the last 2 bytes of your RX FIFO, so that whenever you read out a packet, you automatically get these RSSI, LQI, and CRC check included. So all this, once again, is just to automate and reduce the amount of transactions you have to make through the mailbox to the radio. And so what does this mailbox look like? We have, we called it the RF1A. RF makes sense, 1, it's sub 1 gigahertz, and A, it's our first one. The RF1A interface is essentially for, I guess there's more registers than these 4, but you can think about it as these 4 registers, right? And it parallels almost with a SPI because it has an instruction register where pretty much you pass your instruction, and you can have different kinds of instructions, right? If you look over here at the radio core, so the 430 and the radio core, you can send a command strobe that's going to change the state of the radio. So you can change between idle, receive mode, transmit mode, calibration mode. You can wipe your FIFOs, etc. So that just changes the state of your radio. You can have write and read commands to the configuration registers of the radio, and you can access your RX and TX FIFO. So that's kind of how I group the 3 different radio commands. And you pass those through the instruction register. Some of these are going to require that you provide data. If you say that you're going to write to the configuration registers, then you need to provide the data to write to those configuration registers. And for every for every instruction and piece of data that you provide in, you receive, or for every instruction that you provide in, you receive a status byte out. For every piece of data you provide in, you receive a data byte out, right? And if you provide an instruction that says, I'm going to write a piece of data, then you have to provide that data right in. Else you get an error, which makes sense. I mean, it kind of keeps you honest, if you will. But for everything that you put in, you get either, for every instruction you provide in, you get a status byte out. For every piece of data you put in, you get a piece of data out, which means if you want to read from the radio, you have to provide a piece of data in, right? You have to say, I'm going to read in my instruction register. I'm going to provide a piece of data so that I can actually pull that piece of data that I wanted out of the radio. All right. And this kind of breaks it down a little bit more for you in terms of how you access this mailbox. You have an instruction word register, which combines the instruction byte and the data in byte. So you can either write it as 2 bytes, meaning you write the instruction first, then you provide the piece of data, or you can write it all into one register. It's word or byte accessible. And the same goes on the status and the data out bytes. We actually, since it has kind of this almost spy behavior where you provide a data in and you get data out, we implemented an auto read feature. So you can provide an instruction that you say, instead of providing a data, having to provide a piece of data in, you can just say, hey, I'm going to read the radio and automatically read that data byte out, to try and simplify the process. And this, I think, just shows it in a different way, that you have the byte and the word addressing. So these here are the logical channel errors that you can have between them. I said that that RF1A tries to keep you honest, and it does through these logical channel errors, which can either trigger an interrupt, or they can trigger, or they can just set the flag that says, hey, something went wrong. And so if you provide a piece of data in, if you tell the radio you're going to provide a piece of data, but you don't provide a piece of data, and you just write another instruction, you're going to trigger an error. Or in fact, you actually, sometimes a radio, let's say it's doing some kind of calibration on its way to transmit mode, right? And you start providing it data to the TX FIFO. It may not be ready yet, so we actually have ready flags on the radio that say, hey, I'm ready to receive a new instruction. I'm ready to receive new data, ready to give you new data for you to read out new data from the mailbox. And so you got to make sure that you're checking these flags so that you're not violating, I guess, any of the timing of the radio as it changes between the states. We also have flags for that, right? There's also a low voltage error. It should be noted that the LDO has different core voltage levels for the MSP430 on the 5XX core, and you need a core voltage level of at least 2. So if you don't have a core voltage level of at least 2, it'll trigger this error. It says, hey, you're not going to have enough juice for the radio. And then, of course, you have the interface and the interrupts. So the interrupts come from 2 different places, from 2 distinctly different places. You have the interface, which we were talking about, that's the instruction, data in, status, and data out, which means, hey, I'm ready to receive a new instruction, I'm ready to provide you new data, or things of that nature. That comes from the RF1A interface, or the mailbox. Then there's the interrupts that you actually get from the radio core that says, hey, I've received my status byte, I've sent the last byte of the packet, I have my TX FIFO has overflowed, or has underflowed, my RX FIFO has overflowed. These are different sources of interrupt, but they both source the same interrupt vector. So the same interrupt handler is used for both the RF1A interface and the interrupts. And you just have to check which one you want to prioritize, if you will. So that was a whole lot. That was a real deep dive, if you will, for what is in the CC430 in terms of the radio, how you communicate with the interface. Hopefully that gives you a good idea of what you're going to be doing if you're actually working with these devices. I want to show you real quick the different derivatives that we have. We have them with and without the LCD module. We have up to 32 KB flash, 4 KB RAM, but then you've got different flavors, 16, 8, 2 KB RAM. And then, so all of this material is available online. In terms of size, how much space savings do you get? The 64 pin, which is actually all the LCD parts are going to distinguish the 64 pin, are going to be 9x9s versus 7x7s for the non-LCD parts. The 513X parts, 5XX parts, non-LCD, 6XX parts, LCD, right? So you're either looking at a 9x9 QFN or a 7x7 QFN. And so, of course, we provide a lot of tools to try and make it easy for you guys. The slide has a lot of writing. For the sake of time, I'll move through to the tools you'll be using actually when you're using the CC430. The evaluation module. So this is available today. You can go online. You can order it. This is actually I think it's a previous revision. We have one latest, but it looks exactly the same. Point is, you can use this to communicate with the CC430, kind of start your project development. You've got these headers, which we provide headers for. We provide the little pins that you can solder onto there. And we bring out every pin on the device, of course, except for the RF side. But it's cool because you can use this as a reference design for a whip antenna. And so you can, we have code examples for this that you can run RF code examples that show how to communicate with the radio. You have the example for the whip antenna, the reference design, schematics, layout. We got it all. You can measure the current consumption here using one of these pins. You have both access to the BSL as well as the JTAG. And so that's the tool you'll be using. It comes, the sample kit contents come with 2 of these guys because one of them does you no good. You have 2 antennas, battery holders so they can operate wirelessly, the 2x4 pin headers that I was talking about to get a hold of your signals, the 232 kilohertz crystal, and the documentation. All of the documentation you'll actually be pointed online because it's available online. SMARTRF Studio, very cool. Definitely recommend that you get it, that you download it for the CC430. It's pretty much, we talked about this wide array of configurability that the CC1101 has. Am I still on the, hold on. All right, sorry, I thought I got kicked off there. That the CC430 has different frequencies, different data rates, different bandwidths of the channels that you want to select for each one of those. We've done all that work for you, and it's all graphical. You can just say, I want to operate at this frequency, at this data rate. I want it to look like this, and it outputs a big .h file that you can use in your application that has all the radio configuration register settings. It's also kind of a cool tool if you want to use it for evaluating your RF front end. Let's say that you design your own CC430 and you actually just want to see what RSSI you get at certain distances. You can do this all automatically without writing any piece of code. So SMARTRF Studio, remember it, use it, and use it along with the EVM tool that I just showed you. If you use Simplicity, it's a TI proprietary protocol that we have. It supports the CC430. We have a packet sniffer for it. And Simplicity is star configuration capable, but it's also really good at just peer-to-peer. Pretty much has an access point, which is your network coordinator. It can have repeaters. It can have end devices. Those end devices can sleep. So it's an ultra-low power, very small footprint, easy, just very easy to learn networking protocol in terms of the API. It's like 7 instructions. Definitely recommend if you want to get started and you want to see something work, plug in Simplicity or any of these other protocols that we'll make available through our third-party page. You guys will see plenty of that coming up here in the future. We got a range of application notes that supports the CC430 and these other different options in terms of, we have a wiki, an E2E forum, which I think has become more popular. You can email us at support@ti.com or check out any of our pages. We got a whole bunch of information out there. So hopefully you guys enjoyed the presentation. And I see we have some questions down here. Is it possible that in the future we will have CC430 processor working on 2.4 gigahertz? Oh, okay. So that one's answered by Prentice. You guys please check that out. I have two questions. MC unique ID and CC430 family. Where in the memory can I find this ID, an address? So that you want to check out the data sheet because yes, it's also in the 5XX, so 5438. You're pretty much looking for TLV. We call it the TLV. And the data sheet outlines specifically. I believe it starts at hex 0x1A00. That's the address you're looking for, so go check it out. Does AES encryption module come under export controls? Yes, it is controlled by export policies. As long as you don't live in, like, I don't know, Iran or Cuba, or you're doing military applications for foreign countries, I think you're okay. And all of that stuff is handled automatically whenever you create your TI account. You specify where you're from, and then we have a special export number that we use to send to you guys. So it's, I know that in some countries you do have to get export licenses for the encryption. So it's something you should become educated on if you intend to use encryption. You can't just use encryption like anything else. It's strictly regulated by many countries. But you know, we do what we can on our end to make it as easy as possible to ship to you. And you know, I should probably write a wiki article about that, honestly. But it does come under export controls. Is it possible to boot and reprogram the device wirelessly? It is. It's the question you have, it usually comes down to memory, honestly, because depending on the size of your application, you're going to need to keep a current working application and then a second image of it. So we see some solutions that have an external EEPROM, for example, or if you have a real small application or a piece of the code that doesn't need to be reprogrammed and you partition it appropriately using your linker command file, then maybe you can manage that. I know it's tough. It's not easy, but it's definitely possible to do so. And you know, in fact, if you're really clever, you'll fit it into that BSL memory. You'll lock it down, and that's your new Bootstrap loader, right? So, may I get your email? I think I need that if I encounter problems. I guess in this forum, I wouldn't necessarily give out my email. It's a good question, but you know, TI. I monitor the forums that we have externally in terms of the E2E periodically. Support at TI.com comes to guys who sit right next to me. They come and they ask me questions. If they can't answer it, we've trained them up. We really have, I feel, a good system. In many cases, maybe your company has some direct support from TI. So start with support at TI.com and work your way in from there. I guarantee you will get an answer to your questions. Once again, the E2E forum, I think, has been a very successful method of providing support to our customers, reusable. So there may already be a lot of information there for you. So I believe that's all the questions I see. I'm going to refresh one last time. Oh, okay. Where can I find application examples? These are online. Okay. Applications examples are, go to TI.com, just go to TI.com, and then in the top right, type in CC430 F6137, and you're going to get a product page. And this product page is where you find everything, pretty much. Or if you just type in F6137, if you just type in, you also get the product page for the EM module, which has some other information there in terms of the reference design and all that. But the code examples can be found on the CC430 F6137 product page today. SMARTRF Studio, also CC2500. Yes, it is useful for the CC2500. Of course, you need the hardware to back that up, which is the SMARTRF05 hardware. And I think that's it. Thank you very much for your attention and for joining us today on the eTech Days. I thought it was a lot of fun, though I didn't hear any of you. Hopefully you enjoyed it. Have a good day.